So this is part B of 5.52. Again, we're in this situation where we have a tire, and the life of this tire in miles is distributed with an exponential distribution with a mean of 30,000. And then we calculated that the survival function is given by this right here. So now we're asked what the probability that this x is over 30,000 miles, given that it is already gone 15,000 miles. So we want the probability that the tire lasts more than 30,000, given that it is already greater than 15,000. So for this one, if we wanted to, we could just use the memoryless property of the exponential distribution. So the idea with that is that we've gone 15,000 already, right? We're sitting, so let me draw this little timeline. So here's 0, here's 15,000, and here is 30,000. So with the memoryless property of the exponential distribution is this. We're sitting at 15,000. We know that our tire's already gone 15,000. We're saying what's the probability that our tire lasts at least 30,000. So it lasts at least another 15,000, right? That is going to be the same as if we were standing at 0 and we're saying what is the probability that my tire lasts another 15,000. It doesn't matter. It kind of forgets this information and it kind of makes this the new 0. And it's saying what's the probability that my tire lasts another 15,000, given that it's already lasted 15,000 miles. It doesn't matter, right? It's going to be the same as the probability that my tire lasts 15,000 miles, from time 0. So what I'm saying is that this is going to be equal by the memoryless property, the probability just that my random variable is greater than 15,000. Right? I've already gone 15,000, so I'm given that my x has lasted 15,000, right? This is saying what's the probability that lasts at least 30,000? That means another 15,000. That's the same as if I was just starting today, I just bought the tire, and asking the question of what's the probability that my tire is lasting 15,000 miles. That's what this is saying. So given that, that's not a very good thing for the life of a tire, right? If I know that my tire has lasted 15,000, the probability that's going to last another 15,000 should be less, right? I've driven 15,000 miles on this tire. Some of the wear is going to be gone, right? That's indicating that an exponential distribution might not be the best model for the life of this tire. But regardless, we're assuming that it is, right? No model is perfect, so this is definitely one pitfall of using exponential distribution to model any type of the length of life, right? So either in humans or in cars or anything like that. The probability as you get further and further, the probability that you live a certain amount of time should be less. But anyways, this is going to be equal to, then we already have our equation there, e to the minus 15,000 over 30,000. So this is going to be equal to e to the minus 0.5. And let's throw that into our calculator. So this is e to the minus 0.5. And I get that this is approximately equal to 0.60653. So there we have it. If you wanted to, you could use the definition, right, of a conditional probability, and I'll write the first line out. I'm not going to actually do the whole thing, but this would be equal to the probability that x is greater than 30,000 and, right, intersection, and x is greater than 15,000 divided by the probability that x is greater than 15,000. Right? And then from there, the probability that x is greater than 30,000 and greater than 15,000, that's really boils down to the probability that x is greater than 30,000, right? If I know it's greater than 30,000, knowing that it's greater than 15,000 doesn't help me at all, right? Because I already know it's greater than 30,000. So I can kind of just get rid of that over the probability that x is greater than 15,000. And then if you do this out, you should get the same answer here. So I can let you guys double check that, but should be the case. So anyways, that's it.